The various chi-squared tests that we find in our text can be a common source of confusion. And so in this video, we want to look at the first of these, known as the chi-squared goodness of fit test, or the chi-squared GOF test. This is used when you want to compare frequency distributions. So in other words, you have a distribution and you want to know whether it agrees or disagrees significantly with a different distribution. You would deploy this test. Now, if you have a later model TI calculator, TI-84 or later, you actually have a built-in function, which you can see here, that will perform this test for you. You'd go to the Stat menu, and you'd go to the Test submenu, and you'll notice that there are two chi-squared tests running on this calculator here, two built-in functions. The first is the chi-squared test, and then the second one, letter D, is the chi-squared goodness of fit test. Now, unfortunately, if you're running a TI-83 or an earlier model, you do not have a built-in function for the chi-squared goodness of fit test. But we will show you a workaround for this towards the end of the video that will permit you to do these kinds of problems very easily on your calculator. In order to illustrate this, we're going to go through a prepared example in the text. And let's get our calculator ready to work this out. Now, these are data-driven problems. And whenever I do a data-driven problem, I always like to make sure I have a clean slate. And so I'm going to clear my lists. If you're using a TI-84 or later, you really only need 2 lists. But if you're using a TI-83 or earlier, you're going to need a total of 4. And so, excuse me. And so now we've cleared our list and we're ready to put in our data. Let's take a look at that data. Here's a problem here. It says, one growing concern regarding the U.S. economy is the inequality in the distribution of income. An economist wants to know if the distribution of income is changing. So she randomly selects 1,500 households and obtains the household income shown in Table 2. So you'll notice that there are 2 lists that are given here in Table 2. And if you'd like to follow along using your own calculator, that would be fine. Please feel free to pause the video and key this in. Just a thing, you know, for some of these problems, they will explicitly tell you the expected counts. In others, they don't. You have to figure them out or ferret them out. They always give you the observed counts. I mean, they have to. But it's the expected counts that are difficult for a lot of people. And so we're going to show you how to do those for this problem. It is written up in the text, but we're going to take a slightly different approach. So again, feel free, pause the video. Let's get this keyed in. If you have everything keyed in correctly, it should look kind of like this. Hopefully the numbers in list 1, which are the observed counts, will look familiar. The numbers that I have in list 2, though, they may not. These are from Table 1, actually, in the text. Let's take a quick look. And so if you look carefully at what I have in the calculator, you'll notice that I've taken these percentages from Table 1 here, and I have put them in as decimals. So what I'm trying to suggest is that if you want, you can follow the suggestion of step 2 here, and you can calculate these one by one. Or if you know how to run your calculator, there's a little bit more elegant and efficient way that you can calculate these expected counts. So let's take a look. So what the text is saying effectively is that for your expected counts, you should key in one by one the scaled to a sample size of 1,500 percentages. So in other words, the expected count that goes in the first cell there would be 7% of 1,500, and then the next cell would be 8.6% of 1,500, and so on. And so there's nothing wrong with keying those in one by one. And you'll notice that that is the first value of the expected counts, 105 there. But there's a little bit more elegant way, and so what I would prefer to do is like this. You want to go up to the very top of the list, and you want to make sure that the name of the list is inverted, as you see. And you want to then put in list 2, which is the name of that list, and you want to multiply by 1500. Now what that's going to do, it's going to multiply everything in that list by 1500, and so it's going to give you your expected counts very quickly, as you can see. And those match exactly what we have in the table. So at this point, we're ready to run the test. And so if you're using a TI-84 or a later model, it's going to look like this. You're going to quit this. You're going to go back to the Stat menu. You're going to go to the Testing submenu, and you're going to select the chi-squared goodness of fit test. And we have everything in place with one exception. We have our observed counts in list 1. We have our expected counts in list 2. We don't have our degrees of freedom. And so if you go back to the text and you read the treatment of this particular example, you'll see that the degrees of freedom are always one less than the number of counts being compared. So in this case, we're comparing counts from 7 categories. And that means that the degrees of freedom would be 7 minus 1, otherwise known as 6. And so with that, we're ready to run the test. And so all you have to do is calculate, and you can see pretty much what you need right here. So at the top of the screen, we have our test statistic. Chi-squared is 10.1052, and so on. Right below that, we have the p-value, which you can see is 0.120, well, 0.03 if you round it correctly to 4 places. And with regard to rounding these, generally 3 or 4 places is sufficient unless they are unusually large or unusually small. In that case, maybe you'd want some additional places for accuracy. Now, down at the bottom, you have a list of contributions. And if you look carefully at this list, you can scroll through it using the left and the right arrows. You should hopefully get a feeling of deja vu all over again a little bit later when we show you how to do this with the TI-83. But as you can see, it's very easy to do this test using a TI-84 or a later model, and you pretty much have everything you need at this point to come to a conclusion. Let's see how we're going to run this, or how we're going to interpret this test. The generic null and alternative hypotheses for the chi-squared goodness of fit test are as follows. The null would be that the fit is good. So in other words, there is no significant disagreements between the two counts, the two distributions. The generic alternative hypothesis would be that the fit is not good. In other words, there is some significant difference or differences between the counts. Now, if you contextualize it for this particular problem, which was about income distribution, the null hypothesis would be that the income distribution hasn't changed. And the alternative hypothesis, which is the bare minimum that we have to have if you're writing this up for an exam question or something like that, that would be that the income distribution has changed. Now, as far as what we've obtained from the calculator, we have our test statistic and our p-value, and those are definitely things we would want to have written down. So let's do that. Our test statistic was 10.1053 and so on, and our p-value was 0.1203 and so on. So again, I've recorded those both to 4 places. So we're ready to come to a conclusion here. If you go and look at the problem we were working on, we were given that the level of significance alpha is 0.05. And so if you're comparing the p-value with that, then since the p-value is larger than alpha, we are not able to reject the null. And so on a practical level, what that means is that the evidence we have doesn't support the alternative hypothesis. In other words, we cannot show with the evidence we have that the income distribution has changed. Now, if you're running this test on a TI-83, everything you're going to write down is going to be the same, but the process of actually testing it on the calculator is a little bit different. Let's take a look at that. Because the TI-83 lacks that built-in chi-squared goodness of fit test, you have to learn how to use the list operations in order to run the test without having to calculate everything by hand. And by that, what I mean is the following. The calculations you see on the screen here are what we are going to have the calculator do for us. And in order to understand what we're going to do on the calculator, you have to understand how the test statistic is built. And so if you look carefully at the test statistic, it is a sum, and in the numerator of the parts of the sum, you have the observed count minus the expected count. We square that quantity, and then we divide that by the expected count. And so we're going to have the calculator do that for us as follows. You need to go back to the stat menu, and you need to go to the list menu, and you need to edit a couple of more lists. Now, everything we have on the screen right now is perfectly fine. We don't have to change that. What we need is we need to use list 3 to build the elements of that test statistic, and then we're going to use list 4 to construct it. And so what I usually like to do is I go up to the top of list 3, as you see there, and I'm going to open up a couple parentheses. I want to make sure that the calculator understands everything. And so if you recall what the test statistic said, it was observed minus expected quantity squared. So observed is in list 1, expected is in list 2, and so I'm going to square that, and then I'm going to close that, and I'm going to divide that by expected, which again was list 2. And so when I press enter, you're going to see that list 3 will be populated by the sum, or the parts of the sum, and then I'm going to use list 4 to add them up. So there's your contributions. And if you go back and you look at what we had on the previous portion of the video when we ran the test automatically, these are the contributions that were listed under that degrees of freedom after we ran the chi-square goodness of fit test. So now we're almost done. All we have to do is go over here, list 4, and we want to add up everything in list 3. So in other words, we're going to use the list ops, and we're going to get a cumulative sum of the entries in list 3. So you do that as follows. You press second stat, you go to the ops submenu, and we're going to take number 6, which is a cumulative sum, and we're going to run that on list 3. And so that's going to populate that list, and you'll notice here, if you look down at the very end, that very last element right there is your test statistic. Now, you could test this using a rejection region if you wanted to, and if you do, I'm not going to say that you're wrong. It is a little bit more time consuming. It's a lot easier if you just remember that value there, and then you use it to get a p-value from the calculator as follows. Now remember, when you run a chi-squared goodness of fit test, it's always a right-tailed test. So in other words, the region that you're going to be finding the area of for the p-value is always the right tail. And so the syntax is kind of the same. It's going to look like this. You're going to quit this, and you're going to go back to the distributions menu, and you're looking for the function that you can see right here. It's number 8. It's the chi-squared CDF, the cumulative distribution function. Now this function has 3 inputs. It has a lower limit, an upper limit, and a degrees of freedom. And so as long as you know those, then you're fine. So the lower limit is going to be your test statistic, because it's a right-tailed region. And so if you want to, you can key it into a little bit more precision. 3 places is generally enough, but if you rounded ours properly, it was a 10.1053. And then the upper limit would be positive infinity, which if you have to key it in, it would be 1 times 10 to the 99 power. That's how the calculator does it. And then, of course, if you recall, our degrees of freedom is 6. And so then you'll paste this, and you can see the syntax right there. And so if you're using a TI-83, actually, you're not going to have that kind of interface where you key in everything one by one. You're just going to key it in like this, and it's going to look just like what you see on the screen. And now when you press enter, you have your p-value, as you can see. And so at that point, you have everything that the TI-84 user had, and you can interpret the test the same way that we did. Hope that helps, and if you have any questions, please feel free to drop me a line. Now we have another example in the next video.